Hello and welcome to this presentation. I will be discussing how we went from SQL to Dgraph and our journey with MissionBase. After growing to over 500 users and implementing advanced access control list, we faced challenges. After struggling to build our own GraphQL implementation, we believed there had to be a better way. We found Dgraph and fell in love. This is our story. Let me introduce myself. My name is Anthony Master. I'm the founder and developer of MissionBase. I have been using Dgraph since June of 2020. I have a bachelor's of theology but with no formal technical training. I'm a self-taught web developer by passion. Besides application development, I am a youth minister and missions director at my church. I have been involved in graphic design and web development since 2007. Let's talk about the idea of MissionBase. It all started with the address book, a spreadsheet, and a lot of time spent on the telephone. Here, let me explain. A lot of my friends are missionaries. These missionaries serve in different countries all around the world. To do the ministry work and support their families, they first must raise funds. These missionaries raise funds from independent churches all across America. They call these churches and book meetings to present their ministry. Many years ago, a few of these missionaries got together and compiled an address book. This address book has since been digitized and copied countless times. Since every person was using a copy, there was no good way to keep all of the address books updated. We knew there had to be a better way. If we could unify all of the users into a central address book, then when updates came in, they could be instantly shared by all of the users. At first, this seems like a simple task. There are various technologies out there that these users could have tried to accomplish what they needed. Some have tried to use Google Sheets, Salesforce, and many other collaboration tools such as Monday.com. But no perfect tool was found. Everyone had at least one of two problems. We needed to ensure our data integrity. We could not risk data being deleted by users on accident. The bigger issue at hand was data privacy. It was not clear at first the role that data privacy played in the user's needs. To understand this better, we had to look at our users' data. Along with a public address book, users also needed to store private contacts, private financial data, private and public notes, and personal tasks. All of these data points were linked together. Private contacts can be linked to public organizations. Private financial data is linked to contacts and organizations. Notes are linked to contacts and organizations and can be public or private. And personal tasks can be linked to public or private contacts and organizations. What we needed was an application that allowed our users to collaborate on the data to keep it fresh and up to date. This application also needed to be secure to keep personal finance data safe from other users. Users also requested that we provide tools to integrate this data with other services to keep their data connected. In about 4 months, we built version 1.0 of this application. We were using a LAMP stack. In this presentation, we were mainly discussing the MySQL portion of this environment and the problems we faced. To keep our users' data secure, we decided to namespace each user to his own database. We had a database to manage users, a public database to store and manage a public address book, and every user had their private database to add in their secure data. This was very secure, but became very complex. Growing to over 500 users, we had over 500 databases to manage. We quickly realized that our application was hard to scale, hard to build features, hard to fix bugs, and hard to analyze. Every time we needed to change the schema, we had to replicate that change in every database. Finding out how users were utilizing private features was very time-consuming because we had to query each user's database individually. Then came the biggest challenge we faced. We needed to add new team features. We wanted to allow our users to work together in smaller groups or teams. Teams should be able to import existing data, and we will enhance it with our third-party APIs. Teams should be able to share contacts privately. Teams should be able to limit their display data to only the data their team has verified. Teams should have ways to work together, such as notifications to other team members. Teams should be a first-class feature with premium support and future enhancements. Teams should no longer be dependent on email rings to get the data they need to share. Teams should be able to add custom fields to customize the application to suit their needs. Teams should be able to integrate their data with their pre-existing third-party applications, such as their financial systems. And lastly, team admins should be able to control the access to the teams and granularly control the rights of each team member within their application. We were excited to start building out these features, but we faced a big challenge. Where do we put all the team data? If we add the team data to the public namespace, then we cannot secure it. If we add the team data to the user's namespace, then we would have to replicate the data for every user. If we created a new namespace to hold all of the team's data combined, then we risk the problem of teams accessing other teams' data. We could have created a new namespace for every new team, but we were imagining exponential growth and we were not able to scale that model. There was really no perfect place to put team data. We needed to rethink and redevelop our data storage strategies. Up to this point, we were dependent upon the database to provide data security. For team features, we would need a way to granularly control access to a shared database. The only way to add access control on a shared resource like we needed was with an API. Many modern web frameworks are client-side only. Data security is not secure if it is left up to the client to perform. Data security was not the only factor, but we also had to think about data integrity. We needed ways to control data types and data uniformity. Data that was not uniform became very hard to manage. We were wanting to eventually build out native applications for users' devices, and we would need a flexible toolset in the API. This last point of access control was similar to the first, but also unique. We needed a secure data, but also needed to be able to granularly control and grant access privilege over that data based upon the authenticated user or application. Looking for the best practices in the API, we realized that all of our data is highly connected. We wanted to query our data in a graph. Our users needed to do deep traversals into our data structure to find the information they need. We learned about GraphQL, which provides a simple API for applications to communicate with back-end services. I said simple API, but that may be the overstatement of the year. GraphQL is hard, especially in a relational world. What GraphQL boasts of being simple and easy becomes very hard to implement. GraphQL is great at providing clients an easy way to ask for the data, but inside the API, resolving the client's queries is completely dependent upon the developer's implementation. The 4 main reasons I found to use GraphQL quickly became the 4 struggles I had with GraphQL. GraphQL makes deep joins look easy. You simply ask for the data as it relates to the parents. But joins in the relational world can cause very poor performance if not done well, and even have very small limitations when done correctly. To circumvent the problem of deep joins, many GraphQL engineers will create the N+1 problem. The N+1 problem is where n additional requests are needed for every parent request. This causes a lot of network traffic between the GraphQL layer and the database. Trying to solve the N+1 problem, we created dynamic SQL joins. This led to many performance issues though. The second issue I had with GraphQL is overfetching. In many of the GraphQL implementation examples I found, developers were selecting the entire row of data when they only needed a single field was being queried by the client. We circumnavigated this by only selecting the fields the client requested. We quickly realized though that what we had fixed in overfetching had evolved into our third issue of underfetching. When we only selected the data that the client requested, then we would have to select the additional data the next time the user requested more data about the same row, even if in the same request. This led us directly back to our N+1 problem. To top all this madness off, we found ourselves writing very complex middleware to solve our team features and secure our data. The middleware logic became not only massive, but it quickly aided our performance. We had to join more and more data together to have the data needed for our middleware algorithms. This cycle was endless. After 6 months, we were 50,000 lines of custom code into our GraphQL API implementation with no end in sight. This was not a good place to be with users that were expecting our new team features right around the next corner. We were a very small team development at this point, with myself being the full-time developer and another developer pitching in part-time. We wanted to build out these new features in an application, but did not have the manpower, resources, or time to do it all ourselves. We had too many layers. We were trying to implement GraphQL layered on top of a relational database, but what looked easy was actually very hard. GraphQL is great in theory, but it fails in many implementations. Instead of making good on its promise to simplify the API, it usually just adds more complexity. The hardest part of GraphQL became the need to write resolvers. Every time the application changed and the API needed to be iterated upon, we found ourselves driving through more layers and thousands of lines of code. All of these lines of code and layers need to be updated separately for each change. We believed there had to be a better way. We asked ourselves the question, if our API is a graph, then why isn't our database? We began a search for a graph database we could build our API layer on top of. We tried many different ones such as Dgraph, Neo4j, TigerGraph, Azura, Amazon Neptune, and JanusGraph. Each database had a learning curve and challenges to face. We narrowed our decision down to 2 databases, Dgraph and Neo4j. Neo4j had just launched 4.0 and was getting a lot of buzz. There were examples of developers writing GraphQL layers on top of Neo4j, which made the resolvers easier to manage. What made the final decision for us was support. We opened 2 support questions on Neo4j's community, which are still unanswered now 6 months later. We opened support questions on Dgraph and were quickly surprised that support was not just from the community, but also from the Dgraph's engineers and even the founder himself, Manish. If I personally have to choose between the option of having support from the community or having the engineers directly, I will choose the engineers every time. I quickly learned that Dgraph support was exceptional because of the values that Dgraph had set in place. So support made the decision, but the GraphQL API sealed the decision. With Neo4j or most any other graph database solution, we would still need to write the resolvers for the GraphQL API layer. Dgraph took the GraphQL API layer and put it into the core of Dgraph itself. There was no longer a need to write resolvers just to do the basic CRUD operations. Now to get to the heart of this presentation, how we transitioned to Dgraph. While studying different graph databases, we came across so many unique graph query languages. It seemed like every graph database had their own language. There was no universal graph query language that every graph database had adopted. Dgraph was no different. Dgraph had took the GraphQL specification as a query language for APIs and extended it to be their database query language. At the time they were calling this GraphQL plus or minus, and I like to call it GraphQL more or less. This eventually became so confusing with the GraphQL spec though, that it was renamed to DQL for Dgraph's query language. The great part about Dgraph was that I did not need to learn DQL to start using Dgraph right away. I did find value in it and use DQL for management purposes, but in my application we are able to purely use GraphQL, which we had already learned. The next transition we had to make to Dgraph was much easier than we expected. We had already developed a quite extensive GraphQL schema. A complete GraphQL schema not only includes types but also queries, mutations, and the inputs and output types. Using Dgraph's GraphQL API, all we needed to do was to provide Dgraph with our core GraphQL types, and Dgraph will generate the queries, mutations, and the inputs and output types for those types based upon the schema directives we provide. Look at this very small type of a person with only 2 fields. Now compare this to the left-hand side of how much schema would be needed for the same API that Dgraph generates. We could not even show all the schema and make it readable on this slide. Dgraph makes schema iteration very easy. The longest part in our transition to Dgraph was writing authorization rules. Other GraphQL implementations leave middleware completely in the developer's hands. We would have to write complex algorithms checking clients' tokens and contexts to ensure that we were honoring the business logic that we needed. Dgraph takes these complex algorithms and turns them into simple rules. The best part about these rules is that you can write them in GraphQL itself. That's right, a query rule that in itself is another query. In this example, we are adding a rule to a user type and only letting clients query users if they have in their token the matching username. When I first tried to use Dgraph though, my biggest struggle was deployment. In my Windows-based environment, I was directed to use Docker to get started with Dgraph, but even Docker at the time did not support my system. We turned to Amazon services to run Dgraph. Deploying an optimized instance of Dgraph can be a hard task. Dgraph was in the middle of launching their database as a service /GraphQL. I was privileged to be one of the early users for /GraphQL. It has since evolved to even more and is now called Dgraph Cloud. With Dgraph Cloud, we do not have to worry about tuning the deployment of Dgraph, and instead we get to focus on our schema and our data. After spending a week learning these things in Dgraph, we deleted our 50,000 lines of code in our own GraphQL layer, and we never turned back. We no longer needed to worry about the back-end architecture. Instead, we can do what we do best, develop the front end of our application. We were using GraphQL and consuming the data, but still confused by what a graph database was. We are very accustomed to modeling our data relationally that sometimes we find ourselves getting stuck inside the relational box. A graph database made more sense when I thought more about a graph. Here we have a line graph with 3 points and a line plotted on an x and y scale. Each dot has properties for that scale that describe the dot. The line connecting these dots together has a label describing it as well. This is a fundamental graph database theory. Every piece of data in the graph could be represented by dots like these. Each property of the data point could be represented as the values on a scale. If we take away the two-dimensional plane, we can realize how 2 pieces of data may have a different set of properties. The connections between pieces of data can be represented by lines with labels identifying the relationships. Probably the most helpful thing I can share with you to help you understand a graph is to understand the terminology. I thought it was so important that I even wrote a post and discuss around this subject. We have trained our brains to think in terms of tables, rows, pivot tables, columns, joins, and clauses. What we need to do is forget most of that and transition to graph terminology. A table becomes a type. A row of data becomes a node. Now in a graph, a type does not hold nodes, rather a node is labeled by a type. This type defines the properties that are available to that node. Back to the terminology. What we call pivot tables need to be thought of as edges. What we call columns or fields need to be understood as predicates. Joins and relational lingo can be understood as subgraphs. And our SQL clauses such as where, has, and order by become inputs and sometimes directives. So now that we had a fully functional GraphQL API to use, we could start building our application. We were only missing one part, our data. We needed to migrate our data from our 500 MySQL databases into Dgraph. This seemed like a big undertaking. We found the initial data migration, though, to be easier than we originally imagined. We needed to write a script that could take our databases and combine them into a single RDF file. We found out that our data translated to around 7 million triples. But what does that mean? What is a triple? A triple is the simplest way to represent data in a graph. Follow me through this example. On the left you see 3 tables from MySQL: the users, contacts, and a contacts have friends pivot table. We are able to represent all of this data in the relationships in the form of triples. Triples take the syntax of subject, predicate, and object. The predicate is a key, the subject is an identifier, and the object is a value. We use blank nodes to identify our rows of data. This allowed us to refer to the same node in other places without having a preset unique identifier that Dgraph later created for us. The _: syntax is a blank node. We use a table name and a row ID for the remainder identification of the blank node. This allows us to refer later to the same imported MySQL row in the RDF file. In this example, the user has a relationship to a contact by the ID of 1. We use the same subject, predicate, and object syntax to represent the relationship between the user and the contact. With the triples, we could easily make two-way relationships such as is done with the pivot tables. After we scripted all of our MySQL tables into a single RDF file, we were able to use a process called live loading to add this data to our running Dgraph database. We could then access our data using the GraphQL API. At this point, our API was done. We were able to complete our API in 1 week, where we had spent 6 months on it before. I will admit though, using the GraphQL API from day to day is still not everything I dreamed it can be. There are a few features I still find missing. However, when I look at what it is compared to what I had before, I'm very grateful for everything that Dgraph does for the application developer. It would be unfair to you if I did not mention the features I find missing as of right now. While I review these, I remind myself that Dgraph's GraphQL API is just last month 1 year old. I think it is the most advanced 1-year-old I have ever met. I would like to see in the near future edge filtering. Right now we can filter nodes by properties of the node itself, but are unable to filter nodes by the property of related nodes. This is mainly due to the fact that the GraphQL spec does not support var blocks that Dgraph has extended DQL to use for such queries. By rearranging the structure of the query or applying a cascade directive, developers can still achieve the same functionality. I would also like to see work done to make ordering better in the API. Right now I can order by predicates of the nodes, but I cannot order parent nodes by predicate values of related nodes. I find myself sometimes struggling to redesign my schema to put more fields I want to order by in a parent node that I ideally want to be in a related node. And there are other features as well that would be very nice to have, but are not blockers that I can somewhat easily work around in my client. These include support for arrays holding duplicate and order values. Right now all arrays in Dgraph are actually stored as what many would describe as set. I would like to see actual JS hooks for pre and post mutation. This is being worked on right now. This still looks to be a promising feature to allow users to hook into the generated resolvers with their own custom middleware for even more complex business logic. And then I would also like to eventually see more string functions, datetime functions, and API generated timestamps. All of these things are features that I can work around right now on my client while Dgraph works on making the generated API and the database service even better. Without further ado, let me show you what we have been building. This is our application as of recording in its beta form. I do not have time to do a complete walkthrough, so I'll just show off a very few quick features. We have started right here with a table view of our contacts. We could switch views to see these same contacts in other views. We plan to build even more views in the future. Of course, we can search our contacts by name in the search bar, as well as sort and select fields we wish to see. We can open a contact's mini profile by selecting the contact. I'm going to close this back for now. In the hideaway sidebar, which we can pin in place, we are able to select a different type of data to work with. Below the data type selection, we have our sources and filters. The contact source or list includes our team features. Contacts can be owned by a team and shared by other teams. Selecting a list of teams here changes the source of the contacts to only show contacts from the team of those sources. What I really want to show you though is the filters. We created a filter builder user interface that allows users to build their own filters. In this builder, a user selects either predicates or edges to add filters upon. In our filter we copied, for example, we see that we are filtering contacts by their type and also by their address state, which is in the edge. These filters can be combined with different logic and even nested with additional filters to make very complex filters. If we go back and apply this filter, we can see that the only contacts that match this filter are returned in the main view. These filters can be hidden and rearranged to adjust a view to the user's preference. We don't have time to show off more of our application's user interface, but we're excited that we are able to spend more time now building out this application instead of building out the API. Thank you for your time, and a big thank you to Dgraph for allowing me to give this presentation.